Yes. All right. So this is the alcohols that we first saw a little bit about when we talked about alkenes. One of the reactions of their alkenes made alcohols. I gave you the formula for it. I gave you the name for it. We were able to figure it out. And I think there's maybe one or two even on the worksheet you guys had it to. But now I'm going to give you the real notes on how to name them. Okay? We'll start with nomenclature on alcohols. All right? And I'm going to give you some notes on how to name the harder ones. Oh, I give you the wrong paper? Okay,
Yeah,
hold on a second.
A6.
Oh my gosh. We have to
No, we were on
back.
A6.
Where did they
Just That's the wrong date.
Reactions of alcohol. What date did I give you?
Reactions of alcohol. A6.
Oh, reactions of alcohol. We need preparation now. Hold on.
Come on, back up.
Or on.
What are you doing?
Oh, here they are.
Oh my.
Yeah, just keep those. We'll use them. Actually, we won't get to them until like probably Friday because we have a lab to do several days.
Hang on.
Is this distilling yet? Is that what this is?
Yeah, but we're gonna I'll be talking about it later if we get time.
Distilling alcohol.
John, I need one.
Can I give it to you?
No.
All right. So nomenclature. Here we go.
Who taught you that word?
Again, nomenclature just means naming system. And I'm going to go through the system, and it's basically very similar.
Forget that, right? You actually forgot that. Yeah, I did. Oh my gosh.
All right.
Bye, Victor.
Okay.
Small person.
Now, the naming system for alcohols we're pretty much familiar with it from naming alkenes and from naming chloro or alkyl halides, whatever you want to. We've already learned the system, the basic rules, the prefixes, the suffixes. So here's what you do. The first step says name the alkane and all that that implies. So if the alkane is, 2-methyl, 3-ethyl, whatever, you name it that way. You know how to do that. Hexane, butane, Dayton. Write that down. Hello.
I don't know what's going on here.
Okay. All right. So that's the first step. The first step is you name the alkane the way you always would. Number 2, you're going to number the OH group. Kind of like as if it was a double bond or if it was a chlorine or a fluorine or a bromine on there. You know what that means, number it. You give it the lowest number possible. And by the way, in this case, the OH is going to take precedence over the other things that you've seen for the most part. We're going to talk about other guys, when we have more than one of these together. Say we had an OH and a double bond. We'll talk about that, but not in this chapter. We're going to keep it simple. This chapter is only going to have one basic thing in it per compound. You're not going to have to worry about when you have multiple things. We'll see that in the next chapter. So you number the OH group. You give it the lowest number possible. It takes precedence over the methyls and the ethyls and the chlorines or whatever. Then you add the OL suffix. Here's where it differs a little bit from naming, say, a halogen, where we would call this somebody maybe 3-chlorohexane. We're not going to call this, the number isn't going to be 3-ol, it's not going to be 3, the ol is going to go with the N. All right, so for example, one of the ones you're most familiar with would be ethanol or 1-ethanol. So the number is associated with the OL, with the OH where he is, but you don't put him as a prefix, you put him as a suffix.
So
all right,
like ethane, it would be ethanol.
Right, exactly. Instead of ethane, it's ethanol. So you lose the A-N-E and you make it A-N-O-L. All right, and I'll do 3 examples for you, but there's a 4th thing that I didn't actually put in my notes for some reason. The 4th, I don't want blue, I want black. The 4th thing I want to tell you was you often can get multiple OHs in a group, and I can show you where you have to add just a di or a tri or whatever. All right, so use the di or tri prefix for multiple OHs. Okay? And that di or tri does not go where you might expect. It actually goes right before the OL suffix. And I'll show you with an example in just a second. I'm going to do 3 examples on the board here. One other thing before I give you those examples, if you look up above, right there in your paper, I've got the general formula. You realize we're going to have about 12, Roman numeral 12 or 13 or 14, I forget. Lots and lots of different kinds of organic compounds we're going to talk about. For each of them, they're all going to have some functional group, I'm going to call it. In this case, it's an OH group that gives it its properties and gives it its name. Alcohols have OHs in them. That's what makes it an alcohol. So first, we're really seeing a functional group. Up till now, we only see, even though we're on Roman numeral 4, what have we seen so far? Only alkanes, alkenes, and alkynes. They're pretty much all just chains of carbons, just different kind of bonds in them. Now we're actually adding some weird stuff onto there. All right, OHs. It changes the properties a lot, which we're going to talk about in a minute. But let's just get to some examples of how to name them. Let's start off with the simplest one. What would be the simplest alcohol I could have with the fewest carbons? What would it be?
Methanol.
Yeah, it would just be methanol. And that's how you would name methanol. I don't even need a 1. Okay? If you put a 1, I'm not going to take off points for it. But I don't even need a 1, methanol, because it's the only thing it could be. Same thing's true even for ethanol. You always go by, it's only one place it could be. You always go by the lowest number, too. Now, my second example, I'll make it a little bit larger. Okay? What if I gave you that? On that thing. Okay, what if I give you that guy? Well, the biggest problem you'll see here is which side I number from. I'd already given you the hint, and you kind of know it. I got to start from the right side because the OH is on that side. Even though the methyls will be lower numbers on this side, OHs take precedence, so I would call this guy 1, 2, 3, 4, 4-dimethyl. Four dimethyl, what? 2-pentanol. Okay, see it?
What is the OHs? What hydrogen is the OH on the end one or the one?
This OH is coming off of the second one.
Okay.
That's why it's 2-pentanol. If it was on the end one, it would be 1-pentanol. All right, and the last one I want to do is actually a compound you are familiar with. Actually, you may be familiar with. I don't know if you do much work with your car. This stuff here, and I use this, it's basically antifreeze for RVs. Yeah, well, there you go. It says it right on there. RVs. And the reason you use this is that it's actually not toxic, not considered toxic. You can use this one, or you can use this for your cars. Actually, it's probably a little bit better, but it's toxic. You wouldn't be able to drink this one. Oh, you shouldn't. I don't think you should drink it. Yeah, why would you drink it anyway? Exactly. Anyway, the compound I'm going to draw for you here is the one that's in that antifreeze.
Antifreeze.
And there he is. This is example 3. And how would I name him? Now, he does have he has 2 OHs in there. Okay, this is the one that's in the RB antifreeze. His common name is propylene glycol. And you actually may find him, I was just looking up online, you may find him in a lot of products. It is considered non-toxic, and so they do add it to a lot of things. I was surprised to find it's the products that it's actually in, because it's considered less toxic. But you won't find ethylene glycol in those things. But this guy, his actual name is what? It's not, what would you call this guy? You have to number the OHs.
1, 2.
1, 2, this is kind of weird, propane diol. Okay, 1, 2, propane diol is how you would name that guy. And the ethylene glycol would have been 1, 2, ethane diol. Ethane diol, I mean. Okay? Not ethane. So they're very similar, and the reason they're used, the reason I show you this guy, actually, and the reason I wanted to do this one has to do with the properties of alcohols. Turns out there's 2 major things that determine the properties of alcohols. Because remember, in this chapter, I'm going to have 2 tests. One's going to be on the reactions, which I'm going to start going over in a minute. But I'm going to first talk about the properties. Okay? And going back to these antifreeze and coolants for your car, let's talk about these properties. They depend on 2 factors. All right? Now, 2 factors they depend on are, of course, how many OHs you have in proportion to how many carbons you have. Okay? So the number of carbons and the number of OHs are the 2 basic factors. You already know what carbons do. These are the kind of questions I'm going to give you on the test. Think about it. I drew this on the board when I first went over alkanes. how the longer the carbon chain, the higher the boiling point. But then I said boiling point decreases with branching, remember? So we already have two factors that determine boiling points. Another one to do with boiling points will be OHs, okay? We know more carbons mean a higher boiling point. We know more branching means a lower boiling point. How do you think the OHs are going to affect boiling point? And we also talked about solubility. How will the OHs affect solubility? Think about the carbon compounds. The carbon-carbon bond is obviously nonpolar. Like dissolves like. Water is very polar. So if it just has carbon in it, it's not going to be very soluble. But if it has OHs in it, what do you think of like dissolves like? What is OH kind of like? Like water, right? Water has OHs in it as well. As a matter of fact, they both have what are called hydrogen bonding. Remember hydrogen bonding from Chem 1. All right, so let's look at these two factors. The first one is the number of hydroxyl groups, that is the number of OH groups. Hydroxyl groups are just OH groups, okay? So the number of OH groups. And basically, here's what I could say about the number of OH groups. The more OHs I have, the more soluble in water he's going to be. That makes complete sense. And the more OHs I have, the greater the polar portion, all right, that's why it's more soluble, and the greater the boiling point because of the hydrogen bonding, the extra hydrogen bonds. Hydrogen bonding being the very strongest of the intermolecular forces that you're going to see. Still not as strong as the actual covalent or ionic bonds you're going to see intramolecular. But the intermolecular forces, hydrogen bonds, very strong. Hence the reason we use ethylene glycol and propylene glycol as coolants in our cars. Why would I want to use that as a coolant or an antifreeze? If you remember from Chem 1, adding a solute, any solute, will extend the liquid phase of something by making the boiling point higher and the freezing point lower. But especially the OHs in here make a higher boiling point because it's going to be held together tighter. So that's why we add coolant, Presto, whatever, to our radiators in our cars. We don't want the water to turn into steam, to vapor, because then the temperature can get higher, hotter and hotter. Water, as it's being heated, absorbs a great deal of energy. So we want to keep it in a liquid phase longer, so we add the Presto to it. We add the antifreeze, the coolant to it. Now, the other part of it is the number of carbons. I would expect that small alcohols, like, for example, methanol, we saw a minute ago, I drew, and ethanol, which you're making right over there, right? That's what we're going to do tomorrow in the lab. Those guys are completely soluble in water, and it makes complete sense. The amount of OHs they have versus the amount of carbons has, a lot of OH versus the amount of carbon. So you're good. It's going to dissolve in water. But the more carbons I get, the more nonpolar it's going to be, and the less it's going to dissolve in water. However, so it's kind of the opposite, obviously, from the number of hydroxyl groups. The more carbons, the less soluble. The more OHs, the more soluble. Makes sense. But the other side you got hasn't changed. The more carbons is still going to increase the boiling point. Okay? So the more carbon groups there are, the greater the nonpolar portion, and therefore the less soluble. That's obvious, and it's also opposite of OH, hydroxyl groups. But the more carbons I have, still the higher the boiling. Both of them increase the boiling points. So if I gave you two compounds, and I include the factors we've already learned about with solubility, number of carbons, the branching, and the OHs, you should be able to tell me, given two guys to compare to, who's going to have the higher or the lower boiling point. That's going to be the goal in one of the portions of the test. Now, obviously, that will not be on the reaction portion of the test. It'll be on the other part. There's going to be two tests on this.
Where are you going to put the essays at?
Probably, not on the reaction portion. That's going to be the longer portion. It'll be on the properties and on the essay questions will be on the properties and stuff like that. Okay, we got that?
Yep.
Okay. Now, let's get to the reactions because that covers the properties, it covers the naming. All right, let's talk about the actual reactions. And we're going to start with preparation of alcohols. Okay? Going pretty quickly here because I got to get you guys back to the finish setting up that lab for period 1. All right. How do we make alcohols? Well, you've already seen, believe it or not, you've already seen 2 ways to make alcohols. Okay. That one was underneath carbon monoxide. Remember in the chapter, the very first chapter, we talked about carbon dioxide versus carbon monoxide. And this one is a specific reaction that can only make one kind of alcohol. I'm only going to make methanol. And by the way, you're missing 2 little things on here. Okay. All right. You're only going to be able to make methanol from reacting carbon monoxide with hydrogen. Okay, so it's a very specific reaction. This is not a general formula. All right. And you heat them up with a catalyst, pressure, and you'll get methanol. We talked about him 2 chapters ago. Now, that's a specific reaction. We've seen specific reactions before, last week, for bonus points. Calcium carbide plus water, remember? It made ethine. Okay, you guys, I forget who got the bonus point, but somebody got the bonus point in here. All right, for getting that correctly balanced. Now, the second one we've also seen, I believe, hydration of alkenes. Where have we seen hydration of alkenes? Now, don't do this, but if you turn back a couple of pages, you will see under reactions of alkenes, number 3. You don't have to do it, but trust me, it's there. That's the first place we saw alcohols, and I named it there for you. And there was even an example of that on your worksheet. I told you it would be there. It wasn't hard to name. All right, it certainly wasn't a diol or anything like that. So we've seen these 2 already. Now, the one I want to talk about and do a demo for you, it's a pretty cool demo. You're going to like it. I'm going to do on this one. I think you are. Hydrolysis of alkyl halides. So sometimes people see that word, alkyl halide, and they say, what the heck is that? I've never seen that before. You have to, again, use some common sense. You have seen alkyl halides before. An alkyl halide is just an alkane chain with some halogen on it, chlorine, fluorine, or bromine. Now, you've seen a lot of those. You guys have named those. You know what they are. All right? That is an alkyl halide, right? A fluorine or a chlorine or a bromine on it makes it an alkyl halide, and you know how to name them. I mean, 1-fluoro, 2-chloropropane. All right? So, if I do this to an alkyl halide, if I react him with sodium hydroxide, look what happens. It's exactly, I mean, a lot of what I like about organic chemistry is how much it makes sense versus, just memorization. It just makes sense that this would happen if you look at it. Okay, watch. Here's your alkane chain with the chlorine on it. Here's your NaOH. The OH kicks out the X. The X and the Na get together and make sodium chloride, sodium bromide, whatever. And the OH attaches on there and makes an alcohol. Okay? I mean, that's basically what happens. A lot of this stuff just makes sense. Now, this is the one I have the demo for. And it's a pretty cool demo. Let me show it to you. Watch. I'm going to take, and by the way, remember the point of demos are several fold. Put that light on so you can see it better.
Did we do this one?
What's that? Nope. No, we certainly have used this before. This is a stirrer, an automatic stirrer, and we've used that in a number of demos. I've used that. Okay? I'm going to put about 100 milliliters of rubbing alcohol, basically, and that's the solvent in which I'm going to carry the reaction. I turn it on, and you guys can all see what happens when you do that. Okay, you get a little tornado. Now, I'm going to add to that. Well, what do I have to add to it? I have to add sodium hydroxide and some alkane with a halogen on it. So remember, the purpose of doing these demos is really multiple. 1, breaks it up, not so boring. 2, it's going to reinforce the concept. We're going to do an example for you. But the third one is probably the biggest one. You guys kind of forget that these things are real. You do these things for so long. You draw them out with just C's and H's on a paper, and you kind of start thinking of them that way. But they're real things. Okay, this is 2-bromo, 2-methyl propane. This is a compound. All right, you can smell it, you can see it, it's a liquid. All right, and I'm going to use it in here in a second. All right, let's start off by adding some sodium hydroxide to this guy, because that's what I need. I need sodium hydroxide. All right, now how much do I want to add? Let me look at my paper here. I think it's 10 drops. Yeah, 10 drops of sodium hydroxide. Ready? 1, 2, 3, 4, 5, 6, 10. 10 drops. All right, so my sodium hydroxide's in there now. Remember, the alcohol that I have here, the isopropyl alcohol, is just a solvent when I'm going to carry this out. Exactly, sodium hydroxide being basic. And because of that, guess what I'm going to use now? I'm going to use an indicator, which tells me if something's acidic or basic. Now this indicator, you can see,
What's it called?
it's called a universal indicator. This is not, you guys are used to seeing specific indicators like phenolphthalein, litmus, that turn either red or blue or clear or whatever. This guy is cool because he turns many colors. Ah, that was really cool. Look at that. Well, I'm going to add a whole bunch of this stuff.
Jesus, there goes the whole bottle.
Yep. Now, notice what color it is?
Blue.
Yeah. It's a pretty obvious blue color. And that means, if I look at my little chart here, that means this guy is probably about a pH of about 10. All right, around 10, maybe. Yeah, that's like purplish color, maybe between 9 and 10, 9.5, something like that. So he's very basic. The sodium hydroxide is a strong base, no surprise. Now, I've got my sodium hydroxide in there. I need to add my alkyl halide. And the alkyl halide I'm going to use is 2-methyl 2-bromo. Okay, now you watching? I'll add 10 drops of this stuff in here. 1, 2, 3, 4. Okay? Now,
That's pointless.
pointless. Completely pointless. Nothing happens. Takes a little while, but it will. Keep your eyes on it. All right? I'm going to turn it up a little higher, make it mix a little faster. And you will see, as time goes on here, something's going to happen to this guy. It is. Keep watching. Keep watching. You ready? Now, remember, universal indicator has multiple colors. It can change depending on the pH. And, watch. Green. And, whoa! That was scary. All right. I can make it do it again if you didn't see it. Watch.
I didn't see that.
Yeah, I'm sure you did.
I got 4 eyes.
Okay, back to being blue. And, again, it's reacting. What happens is the OH is being used up. Sodium hydroxide is being used up. And then after it's all used up, it's not basic anymore. Now the pH is around 5 or 6, all right, which is where you would expect it to be because all this sodium hydroxide has been turned into an alcohol. All that OH has now been added on to that carbon chain. Okay, let's turn that light off and do this reaction.
What would happen if you drank that now?
Is it an alcohol?
I'm going to put that paper up here. Things not to ask. We're going to blow anything up today? What would happen if you eat this? What would happen if you drink this? What's another one? How many questions are on the test?
That's universal. That's a universal indicator.
All right. On the test, and by the way, the worksheets I just gave you, a lot of times I gave you the name first instead of the compound. Let's do it that way. I told you what this guy was. He was 2-bromo. Let me use black here. 2-bromo, 2-methyl propane plus NaOH yields. Okay? That's what you have here. 2-bromo, 2-methyl propane plus NaOH. And that's what I might give you on the test or on the worksheet. Now, here's the problem. If you just try to do that using the name, you'd have a hard time. What do I recommend you do first? Draw this guy first. It'll be a lot more obvious, a lot easier to see it if you draw him. Draw him first and see if you can finish him up. I'll draw it for you in a second. See if you can finish him up first. Okay? Now, what would I do first? Well, I would draw the compound. There's it's not propane, sorry. There's propane.
Nothing, it just appeared.
2-bromo, 2-methyl. Well, there's my 2-methyl. There's my 2-bromo. Y'all good with that? Y'all have that drawn?
Yeah.
Good. Plus NaOH. Yields. All right, now what's going to happen? That bromine simply leaves and becomes NaBr, and I add the OH where he was. And by the way, that OH doesn't have a choice. That's where he's going. He's going where that other guy was, right? Got it? Look good? Perfect. All right. Now, the last of the preparation reactions of alkanes we've already done. All right? That's the beauty of this. What is it?
What's the point of doing it again?
Fermentation. And that's what we're going to spend the rest of the next 2 or 3 days on.